All right, guys. So today we're going to talk about limits, and we're going to look at limits numerically and graphically. Now, a lot of this we did in pre-calc, so hopefully it seems familiar. So let's go. So if we have a graph and we're looking at limits, so hopefully you can see this. It says we're looking at the limit as x approaches -2 with a little negative sign after it. That means that we're looking at -2 right here, but we're approaching it from the negative side. So as we get closer to this -2 value, we're about -1.5. Okay, as we approach it from the positive side, it's also about -1.5. And if these two are the same, then the limit exists and is -1.5. And in fact, if I plug it in, we're about -1.5. Now let's look at 0. Okay, we're looking at 0, approaching it from the negative side, which means we don't really care what's happening on this side of the graph. I only care about as I approach 0 from this negative side. Well, that's approaching -1. If I'm looking at it from the positive side, then we're approaching +1. And if the left-hand limit and the right-hand limit are not the same, then the limit does not exist. You might see that as undefined. I'm just going to stick with does not exist because it's fun to say. F of 0, though, does exist. Okay, it's evaluated here. There's an open dot, so that would be -1. So you can have a limit, or you can have a function value without a limit. Okay, the limit as x goes to infinity. So this appears to be approaching a horizontal asymptote there at 2. As we go to -infinity, it's a little bit tough to tell, but it does look like it keeps kind of increasing. This one levels off pretty harshly. This one, from what we can see, I would say goes to infinity. You'd probably, if you were to graph this on your calculator, want a little more information, but let's look at -3. All right, this limit does not exist. It's not approaching a single value. Okay, anytime we have something that's asymptotic like that, unless we were looking at a left-hand limit or a right-hand limit, then that would change. But here, it's not going to anything. And then -5. So here's 5. So as we approach -5, the limit from the left is 0, the limit from the right is 0. So even though there's an open dot there, since they're going to the same place, that limit exists, and in this case is going to be 0. All right, let's look at this step function. So we're looking at the limit as x approaches 1 from the negative side, so that's going to be on this little bar here, so that's going to be 0. 1 from the positive side is going to be 1, and then the limit as x approaches 1, since those aren't the same, does not exist, even though the function value does exist and is 1. Here we have a graph, and what we're taking the limit of is of a composition. So we're looking at the limit as x goes to infinity of, or x goes to -5 of f of g of x. Well, that's going to equal, this is going to equal f of the limit as x goes to -5 of g of x. Okay, so we're going to go to the graph of g. We're going to go to -5. So 1, 2, 3, 4, 5. That limit is going to be 2. So this is now f of 2. And then I'm going to use the graph of f and evaluate. So f of 2 is this little dot up here at 3. So even though the limit at 2 would have been 2, when we evaluate it, it's actually at 3. So limit as x approaches 0 of g of f of x is g of the limit as x goes to 0 of f of x, which is going to be g of, we'll look at the limit as we approach 0. Well, that's at -2. Then we use the graph here. -2 is at +2. Okay, let's do one more. So this will be g of the limit as x goes to 3 of f of x. So g of, looking at the graph of f, looking at 3, is at 3. G of 3, 1, 2, 3, is at -2. All right, piecewise graphs. So we're going to find the limit as x approaches c, and c in this case is going to be 1. So we're going to draw this graph. I'm going to start with when x equals 1, we're at 1, 2, 3, 4. When x is less than 1, so this side of the graph, we're at 3x minus 1. So there's -1, up 3, over. Okay, so it doesn't equal f of x, but that still doesn't mean we don't have a limit. So let's graph the other half of this. So 4x, so that would start at 0 and goes up 4 over 1, so it would start there. So it looked like that. So we'd have an open dot there, which means that this limit does not exist. All right, we're going to graph a function with these different characteristics. So we have a bunch of limits. So as we go to 1, the limit's 4. As we go to 0 from the negative side, it's -1. Limit from the positive side is 0. And then we've got f of 0 is -1 and f of 1 is 2. So I'm going to start with my knowns. So f of 0 is -1 and f of 1 is 2. Then I'm looking at these limits. So this one here says the limit as x approaches 1 is going to be 4. So I'm going to put an open dot there, because if the limit exists there, it means it's going to approach that from both sides, but it's not going to actually equal there. I'll come back to that. The limit as x approaches 0 from the negative side is -1, so that's cool. Just go, okay. But the limit as x approaches 1 from the positive side is 0. Okay, so I'm going to put an open dot there, and I'm going to go ahead and connect it to my 4 and do whatever I want past that. So this has a limit at 4. 1 is 4. The limit from 0 from the negative side is -1. Limit from the positive side is 0, and then those 2 points are true. Now we're going to look at limits numerically by creating a table of values. So we've got this function here, x squared plus x minus 2 all over x minus 1, and we're looking at the limit as x approaches 1. Well, we know the function doesn't exist there, because if I try to plug in 1, it's going to be undefined, but the limit still may. Okay, so I want to investigate 1, so I'm going to stick 1 in the middle, and then I'm going to pick some values a little bit smaller and a little bit bigger. So let's go 0.9, 0.8, 0.7, 1.1, 1.2, 1.3. Okay, well, we can use the calculator to quickly generate a table of values. So on your calculator, we're going to go ahead and plug in that equation. So on the top, x squared plus x minus 2 all over x minus 1. Now you can use the stacked fraction to do this, but if you do that, you may end up with fractions, and fractions are hard to see the pattern in the numbers. Then we're going to go to table set. Okay, so I go second, table set. So my table is starting at 0.7, and my delta, I'm going up by 0.1. Then if I go to second table, there's a table of values. So we're at 2.7, 2.8, 2.9. Error. And then 3.1, 3.2, 3.3. Well, even though it doesn't exist at 1, there still is a limit because these values are approaching 3 and these values are approaching 3. So the limit appears to be 3. To confirm graphically, we'll just go to the graph. And my window's not big enough to see that, so I'm just going to go to a standard window. So zoom standard gets me to a -10 to 10 window. And if I trace to 3, or trace to 1, okay, it doesn't exist, there's nothing there, but if I go to the left and to the right, it sure looks like it goes to the same place. All right, so we have our next one. So we want to look as we approach 0. So I'm going to show you another feature of the calculator. So I want to approach 0. So I'm going to pick values that are approaching 0. So I'm going to get smaller and smaller. So let's say I start at 0.1, 0.01, 0.001. So your table can look different. I'm going to make these negative. And then 0.001, 0.01, 0.1. So you can go even increments like I did last time. We can do funny numbers like this. So another feature, so let me go ahead and enter in sine x over x. We're dealing with a trig function. And everything in calculus, everything is in radians. So you want to make sure that your calculator is in radian mode. If it is not, then you're not going to get the right thing. So always, 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 always in calculus, radian mode. So I'm going to go to my table set again. And I don't even care about this. I'm going to go to, I don't want auto, I want ask. I want to tell it what numbers. So now if I go to the table, there's nothing there. But I can populate it. All right, what's happening at -0.1? And we type that number in, hit enter, and it gives me 0.999. Okay, what if I type in -0.01? It's giving me just 1. Okay, but negative 0.001, it gives me 1. If we plug in 0, we get an error. What about 0.001? 1. 0.01. 0.01. 1. 0.01. Oh, we don't 0.99. Okay, so it's just another way to generate a table of values. If you don't want to mess with the table set and the table delta, is just do ask, and then you can plug in whatever numbers you want to. So looking at our pattern here, these are obviously approaching 1. And if we go to the graph, it's approaching 1. Okay, so now we have the limit as x approaches 1 of this. Well, we don't, this is the follow-up question, right? So we're going to analytically find this limit using what we just discovered, that sine x over x, that limit was 0. So I'm going to rewrite this as x over x plus sine x over x. Okay, well this now is going to be the sum of the limits. So the limit is x over x, that's just 1, plus the limit for sine, which is going to be 0, or the sine x over x, which we just discovered. So this reduces down to 1, and the limit as x approaches 0 of 1 is 1. So we get that. Okay, so we're going to do one more, sine of 1 over x. All right, so again, I'm looking at 0. So I'm going to do those same, let's do -0.1, -0.01. You can make up whatever values as long as they're close to 0. Okay, and I'm going to use the calculator to do those. Okay, so we're going to go to our y equals. We're going to do, rather than sine x over x, we're going to do the sine of 1 over x. Okay, and I'm going to go to my table set. I'm going to go to ask again. I'm going to go negative 0.1. That's 0.544. Negative 0.01. 0.506. Okay, maybe there's a pattern there. Okay, negative 0.001. Okay. What if we do 0? Nothing. What if I do 0.001? 0.01. 0.0, just 0.1. Okay. So here's the values that we got. Well, that doesn't really appear to be approaching the same thing. So it looks like it's going to not exist. Okay, well, let's confirm this graphically. Let's see if it maybe does. We just don't see it in the numbers. Okay, well, maybe there's a limit there, so let's zoom in. Okay, zoom in again. I think it's pretty safe to say that this is not going to hit a limit. As you go closer and closer, it's just going to get more crazy. So this limit does not exist. So we're going to use the function f of x equals 3x squared. So first we're going to find the slope of a secant line containing the points 2, 12, and 3, 27. So the slope of the secant line is going to equal y2 minus y1, so 27 minus 12 over 3 minus 2. So that's going to be 15 over 1, or just 15. So if I were to draw this graph, that would be that slope. Now we're going to do the same thing, but rather than having a specific point, we're going to do this generically. Okay, so the slope here is going to be y2, which is f of x minus x over, sorry, f of x minus 12 over x minus 2. F of x being 3x squared. Okay, so this would be the slope of the secant line, and then you would just plug in whatever value of x you were interested in. Well, now we're going to look at what happens to find the slope of the tangent line at 2. So I want to get infinitely close. I want this point to be as close to this point as possible. So we're going to investigate the limit using a table. Okay, so we're going to have x and then the slope. Okay, so I'm going to do 1.8, 1.9, 2, 2.1, 2.2, 2.3, and then we'll use the calculator. So I'm going to get a new function. So my function here is going to be 3x squared minus 12 on top divided by x minus 2 on the bottom. Okay, I'm going to go back to just a table set. I'm starting at 1.8, going up by 0.1s, and I'll go back to auto. Okay, these are our values. So we have a slope of 11.4, 11.7, no slope there, and so on. So I'm going to copy these values. So 11.4, 11.7, known, 12.3, 12.6, 12.9. So there does appear to be a value that it's approaching, and that value for the tangent line appears to be 12. The next thing we're asked to do is on the same set of axes, graph F, the tangent line to F at the point 212 and the secant line from part A. So 3x squared is going to grow really big really fast. So let's say we go up by, well, we had to get up to 27. So let's make these each 5. 5, 10, 15, 20, 25, 30. That's 20, that's 30. So when x is 0, we're at 0. X is 1, we're at 3. 2 is at 12. 3 is at 27. So there's our graph, and you can use the calculator to help you. Then we have the secant line. Okay, so I'm going to go through the point 2 and 3 there. So my secant line is going to be that there. And then the tangent line, and this graph is going to be a little bit tricky, but the tangent line, it's going to look pretty close to the secant line just because of the size, but it's a one that touches that point and then just goes on. Thank you for learning limits.